Okay, so welcome everybody to this new DaSCI seminar. Today's speaker is Mariia Vladimirova, Senior Researcher at Criteo AI Lab, and I'm a member of Fair Play Joint Research Team with INRIA and DaSCI-UGR in France. She bridges academic and industrial contexts, focusing on explaining and improving machine learning methods through probabilistic and causal statistical approaches. Mariia was named a Rising Star in AI Ethics 2025 by the Women in AI Ethics, a global initiative dedicated to increasing the recognition, representation, and empowerment of women in AI ethics. She's a passionate advocate for gender diversity and inclusivity in technology, actively organizing events that promote equitable opportunities and representation across the AI community, combining rigorous science with a commitment to building responsible and inclusive AI ecosystems. In this sense, today's talk will be focused on causality and fairness in AI. I want to thank again Dr. Vladimirova for very kindly accepting our invitation. And whenever you are ready, the floor is all yours.
Thank you a lot, and thank you first of all for invitation, and second of all for this very detailed introduction. So today we're going to talk about causality and fairness in AI. Why I say about AI, this is a general term, because we will talk about really different applications. So to start with, we will firstly start with definitions and different methods, and definitions on fairness and how it is related to causal methods, and then how we can use the causal approaches for different bias mitigation techniques. And then we will discuss the different kinds of applications and where we can use and how causal methods and causal approaches. So I will focus mostly on tabular data. Then I will give some examples on image generation, then some examples of language generation, and then we will ramp up. So I will not go too much into the details, and I wanted mostly to give like a broader overview of the topic, and maybe to motivate to use causal methods and how they can help with in different applications. So let's start with what is actually fairness. So any question that we want to give a definition, we'll go to the dictionary. And fairness, according to the dictionary, is the quality of making judgments that are free from discrimination. So from this definition, I'm not sure we can really understand what is fairness, because we need another definition. We need a definition of a discrimination. So then let's see what is discrimination. And discrimination means distinguishing between two or more people or things. So when we look at this discrimination, we do not really think that it's a bad thing, right? Because discriminating between good and bad restaurants is perfectly fine. But in this case, when we think about fairness and the discrimination, we really think in our head about something unfair, something bad, and this is because of the context. So because the discrimination based on some of the features that we think should not be used for distinguishing people in specific context, for example, for job opportunities, means something bad, so which is not connected to what we think should be done. And in this case, this system treats differently one group and another, and this means a bad thing. And then in this case, unfairness would be something bad. So to sum up the conclusion, to sum up this definition, is that the discrimination is not always bad, but it depends a lot on the context and on what we do not want to discriminate on. And this is important for the fairness definition. However, it's something vague, and it kind of changes over time because, for example, historically, it was perfectly fine to provide jobs, specific job opportunities only to men, and women were supposed to stay home. And now we don't think this is a correct approach, and it changes over time. However, since it changes over time, there are also different laws that reflect our kind of moral principles. And here is an example that the definition of fairness is still very vague. And in GDPR, different definitions from the fairness word into their language of the law into English means actually different things. So in some languages, fairness was translated as goodness, in others as objectivity, in others as justice, then loyalty, honesty, good faith, and so on. So it doesn't really mean exactly the same thing. And in the end, it kind of demonstrates that even between countries within European Union, we cannot converge to exactly the same definition of what fairness is. And so it makes it hard for the downstream researchers to actually apply our statistics and techniques to measure it. Because firstly, as a society, we have our moral disagreements. Then based on our moral principles, we vote for people who will represent us in the country. Then they create the laws, and then each country has different laws, and then we have conflicting laws. And because of this, we also have different definitions. And based on different definitions in the laws, we have different metrics ambiguity, and then it does not help to correct the bias that exists. So there is no this kind of unification of the approach to fairness. In general, not connected to AI, but based on cultural disagreements, legal conflicts, lack of consensus, and shifting norms. So this just demonstrates the challenges of the problem. Then it translates into problem, into fairness applied to AI models, because we have real world bias, which is also shifting because our moral norms are shifting. Then it's reflected into the training data. And then since it's reflected into training data, it's also reflected into how our models are trained, because they are trained on this data. And then it reflects the output that these models have, because if the models trained on the biased data, they could also be biased, or even have a bias appearing in the model. So despite advancements, persistent biases rooted into the historical inequalities, they stay in the data-driven systems, and this amplifies unfairness and such that divides the societies. So moreover, while the bias appears in the model outputs, now with the rise of large language models, we have even more data generated into the internet, or image generation models. This data goes back into models, into the trained data, and then we have this loop that the biased models even amplify the bias that exists. Okay, so where it brings us. This brings us that we have all these data-driven approaches that is now becoming more and more, having more and more data, bigger and bigger models. So we scale everything, and on the scale, it could lead us to losing more and more control. However, so it's not that bad, because we have research to be done. We just try to correctly state the problem, study where the problem appears, raise awareness on each step where the problem could get into. We have more and more laws that appears because there are more and more models, and more and more impact on the people. And in the end, we have standardization that helps to control this problem. So considering the potential harm that it could cause, we have different approaches that we could get into, help the models to design processes or to reduce harms, or to monitor any changes and how people actually use any models. So Then this is what we could do. And now what is actually happening? So before, let's say 2012, 2013, nobody was talking much about really fairness in AI because the models themselves were not as used. So we're still using a lot rule-based, and then there was this wave of deep learning models that started being working well, and logistic regression is more and more used in industry. And with this famous data set that was released, and people realized that in the US they used the system to identify if a person could commit a crime, and it was biased towards black people. And then people started to realize, okay, AI models can actually impact people in real life. And it was in 2015-16 that the researchers found this bias. And so in 2017, there were a lot of papers that actually defined the metrics for fairness that we use nowadays. And there was a big wave. And then you think, okay, maybe since it was such a big boom, then it continues into be a big boom further. But actually not that much. So we checked in the beginning of the year, the number of papers that was used for generative models, that was used with the a keyword in the abstract or among the keywords on the title, efficient and fair. And efficient, it includes also efficiency, and so on. And so the number of papers that focus really on the efficiency is still growing kind of exponentially. However, the number of papers fairness stays relatively low. And it's like a few papers per conference. And also in a lot of cases, well, it's so few papers that I could check it by hands. And I saw that the fair was quite often in the sense of a fair comparison. So not in the fairness that we would like to have. And so we recently just wrote a paper with the different examples where we stated that so fairness stays a kind of a secondary problem. It's not really paid attention much, at least in the research. Maybe it's like people talk more about it, but not as much as the research done towards fairness or towards improving models. And it feels a pity because we should not say that the model is great if like it's biased, you know. So it's just based on one benchmark, it's not great, but then on the other benchmark, it's amazing. So we say the model is amazing. And there should be a trade-off. And for now, there is no this trade-off. So it's like mostly the focus on the efficiency, and the fairness is like a side problem. Okay, but at least this is what the statistics by the paper says. And then what important is where we want to be in terms of fairness and what we exactly want, what exactly we want to achieve. And here we usually talk about fairness ladder. So the 0 level, the ground level, would be complete unfairness. This is when we give the protected attribute, or this is the feature that we do not want to discriminate on. When we give it directly to the model, and then the model trains based on the data, and then it kind of assigns weight to this feature, to this variable. And this is what we call direct unfairness. Then there is another layer, level 1, which we call fairness from awareness. Is that if we remove one of this feature from the model that we want to discriminate on, the model is used without this feature. However, they still can learn these underlying correlations in the model. For example, when we browse the internet, we do not we do not specify our gender. However, statistically, women browse more like women clothes, men checks more the sports web pages. And so the algorithms, when trying to suggest you, for example, which ad to show, it could unintentionally identify that your browsing attitude, your browsing behavior, and so identify, okay, maybe this is a female profile and this is male profile, and somehow unintentionally provide the biased decisions. So because without bias mitigation techniques, we do not achieve fairness, but this is called fairness from awareness. Then the next layer will be fairness and prediction when we apply bias mitigation techniques. And then imagine we can achieve a perfect fairness in the output, which is generally a very hard task since it's hard to define properly, try to define properly the protected attributes and completely reduce the bias. However, imagine that we can achieve this level, and this is our goal as, for example, as a company, as researchers, we want to build models that do not increase the unfairness. And so it doesn't correct the external bias because we already have the biased world, and then we provide exactly the same opportunities to this biased world. And then it basically keeps the level of bias that we have in this world because it's like providing the same opportunity to men and women. Then there are more men in the senior positions, and then you provide the same opportunity for a senior position to men and women, and with just more men still be on the senior positions. So it doesn't help to correct the external bias, but it doesn't usually doesn't increase the external bias that it has. So as company or as researchers, we do not correct the external bias. However, this is like so-called the positive discrimination to correct external bias, which is also an ethical question to see if it's a good thing or not. And there could be some educational approaches. For example, less women ask for the promotion. So you send an email to all the employees and saying, didn't you forget to ask for promotion or something like this? So this could be like educational approach for everybody, or positive discrimination to correct external bias. And as companies level, we want to be at level 2 because otherwise it could be seen as moral judges. So because to correct the external bias, you provide some bias at individual level. Okay, and here comes the definitions from this causal perspective or individual level, what we actually want to achieve. And then further, I will show the difference between the group level definitions and which actually leads to, which is used in the regulatory frameworks. So for causal mechanism, we usually assume that there are some features, there are protected attributes and the outputs. So here is very simplified graph. We will assume X user features. A would be protected attribute, for example, gender. Y is a true output, for example, if the ad was clicked. And Y hat is the predicted output. And at this stage, we assume that it's already a trained model. So we have a user feature and then what our model predicts. So when we have the arrow, we assume that there is a causal effect. So it means that X causes Y, for example, if there is an arrow from X to Y. Then, for example, the arrow from A to Y hat means that there is a direct unfairness because our model used a protected attribute, gender, directly to learn the model. And so it uses directly as a feature and then provides you an output based on this value. Then there is a indirect unfairness, which passes through X. So there is a causal path from AX to Y hat. And this would be that the model takes some information from X that is a causal effect of A. Okay, then there are other paths that could be seen as prejudice. So when you use data to train the model, which would be A, X, and Y, to train Y hat, Then if you have from a path from A to Y, this would mean that basically the gender defined if you clicked on the ad or not. It's a bit weird, but this is like I'm thinking of the reasoning. I'm a man, so I will click on the director post opportunity like this without any skills or anything. So, and this is like a prejudice, thinking that any man could be considered for the director job. And same happens for the undirect path, but there is a prejudice there. And there is a difference between prejudice, which is unjustified, and merit, which is justified. And so our goal would be to find only the merit path and to remove the prejudice path. So not consider the prejudice path. Okay, and so now how it is connected to the previous framework that I explained based on the levels. Then the unfairness would be that there is a direct dependence between y hat and A. So there is a direct causal path from A to y hat. This would be the definition of unfairness. Then the fact that we remove the arrow from A to y hat, so we don't use A as a protected attribute, and we don't give it as a feature during training, we give only X, the model can still learn the correlations with A and somehow identify the internal correlation, so still have bias because it is the indirect path. And so this is approach called the fairness from awareness. And then the final approach, then we want to get into fairness in the outputs, would be that somehow we force the outputs of our model to be independent of the protected attribute. And from the causal standpoint, it would be equivalent as having a mutual information between y hat and A, providing a different feature to be 0. And so this would mean that there is no causal effect between A and y hat. And usually this is not really possible to get. And so if there is so-called a trade-off between fairness and utility of the algorithm. So sometimes utility can be accuracy, sometimes utility can be well, any performance metric that you can think of. So there are other fairness definitions, and this was based on the this causal graph, how protected attribute and features can affect the output of the model. We can create an actual definition of fairness based on these counterfactual values. So, for example, so-called counterfactual fairness, which is the prediction of the model, and we assume it's counterfactually fair if it would be the same if hypothetical world where the individual had a different sensitive attribute, all else equal, and it kind of simulates a parallel world where the person's either gender and ethnicity is different, but everything else about them stays constant, like skills, education, preferences, and so on. And if the model gives a different result, then that means it's unfair causally. And it aligns with our moral intuition that fairness is about not being treated differently because of who you are. It's explicitly uses a causal model of how feature relates to each other. So like removes the protected attribute that, and tries to fix the others. However, it requires strong assumption on the causal structure, so we need to know which feature is connected. And it could be computationally expensive and harder to scale because you need to have factual and counterfactual worlds. In some cases, it's infeasible. Then there are other definitions which are group related. So this one basically means that we consider the values in groups. And for example, equal opportunity, like a model satisfies equal opportunity if people who deserve a positive outcome have the same chances of receiving it, regardless to which group they belong. And then there is another measure, which is called demographic parity, or the group balance view. So it's a model satisfies demographic parity if the probability of the positive outcome is the same for all demographics groups. And everyone should get the same rate of, for example, ad impression, loans, or job recommendations, regardless of the group. And this is simple, measurable, and these two metrics often used in regulation and monitoring. But limitations is that they ignore why difference occur and can punish models for reflecting real causal differences. So for example, if gender correlates with certain job interests for legitimate interests, it can still say, okay, the model is unfair. Okay, and so to sum up, the demographic parity says on average that, for example, men and women should get the same outcome. And counterfactual says that for the same person, if we could imagine them as a man or as a woman, the model should treat them the same. And so here is where the causality matters, because you cannot talk about the counterfactuals without knowing what causes what. So, and well, here's an example of demographic parity. So the unfair model will have just different distributions for a group of people with the different protected attributes, male and female. And fair model will have exactly the same. Okay, and so further we will see how the causal approaches can be used for in different methods or explain different methods. So starting from now, I assume that Y is a part of train set. So we have A, X, and Y. A can be a part of the train set or not, and we try to learn Y hat. So the first type of method is called pre-processing. It's basically if A, X, and Y are the train set, then let's just remove A from the train set. Or let's just remove all possible correlations with X and Y from the train set, with the A from the train set. And before even starting training, because we know that there is bias in the data. And there are different approaches that do this. So for example, there is data weighting, augmentation, filtering, generation, instruction tuning. But for example, instruction tuning might have limited effectiveness. Then there is a bias in embedding, not necessarily has a bias in the downstream tasks, and so on. And the balance, we still know that even the balanced data sets sometimes lead to different performance disparities because and some biases downstream because of inherent inductive biases. So there were some examples on, for example, prototype degradation and image compression, or image upsampling, and so on. So they tried to do a balanced data set, but the downstream task was still biased. So that means that despite the fact that we can balance data set, or trying to remove all possible biases, sometimes it's either infeasible, either not enough, and the biases still can be found downstream. And moreover, in this case, we need to fix the protected attribute. And sometimes, so if you add more and more protected attributes, then the complexity of the task grows exponentially with the number of protected attributes, and becomes more and more complicated. Okay, then other methods are in processing methods. So this is basically when you train the model and you add some constraints. So it could be constraints on the loss function, could be adversarial training, could be just redistribution. And here we basically try to remove this path that goes through A to X to Y hat, and also from A to Y to Y hat, and from A to X to Y hat. So to try and in this process to remove this connection to Y hat as much as possible. And here, for example, could be adding as a penalty to the loss function. Basically, we're trying to block the information and to have this mutual information between y hat and y in a equals to 0. And then there are post-processing methods when you already trained the model. And then you can add some corrections or fine-tuning, for example, with human feedback or some label adapting, and to correct the model so that it will be fair on the output. So, but however, sometimes it often loses a lot on the performance, or there is some catastrophic forgetting that is happening, could also lead to some hallucinations and so on. So each approach has its pros and cons, and all of them are used in modern architectures. And so currently, different applications, let's say, have different approaches. So there is no really transferability between modalities. Among the technical challenges, we have different fairness definitions. We have limited access to protect attribute. We have not always perfect definition of protect attributes. Some are categorical, some are continuous, some are not even defined. We have fairness privacy trade-off, fairness utility trade-off, absence of public available realistic benchmarks. I haven't talked about it yet, but I'm going to talk about it now. And also quite often we have some claims which are not reproducible from the private organizations, and this also doesn't help the research. Okay, so and now I'll talk more into actual application and how it works in practice. Let's start with table data. So I'm not going to motivate much why we focus on table data, but I wanted to cite a few papers that I believe gave quite a good overview. For example, one is why table foundation model should be research priority. They discuss where tabular data is used. For example, medical applications. A lot of companies use tabular data, including mine. And then there is a recent benchmark on advancing tabular deep learning with parameterization sampling. And then our paper from last year, where we actually released a data set for fairness-aware machine learning methods. Okay, and so there is a lot of need for tabular data, and the methods are not advanced. And in our case, so my company, Criteo, is working on everything around digital marketing and advertising. And for example, the case which is kind of motivating for us is something similar to what Facebook has. And so, for example, in Facebook, you can have job ads recommendations. And it was found some years ago that the job ads in Facebook, they were excluding women from seeing ads. So you could actually select and show ads only to men. And so this year, it was shown that Facebook still discriminates by gender. Actually, just a few days ago in France, they also asked Facebook to prove that they do not discriminate, because they also found some evidence to that. And when we started working on this topic, for us, we also do ads. We also have job ads. However, we do not have access to the sensitive information, for example, gender, because we do ads on the open internet. And so when you browse on the open internet, you don't always say your gender. And so we cannot actually estimate if we have bias or not. But we can have some kind of proxy. So as I explained before, based on the statistics, based on the products that people browse. However, the more practical problems were that when we started working on this, we found that there were not that many benchmarks. So all the methods for table data, they worked only on very small data. And this is because available fairness-aware data sets were very small, like 50,000 lines. And it's not comparable with the large-scale industry data. So then what we did, well, we collected all the data, we privatized it, and so we released it. And it's now on Hugging Face, and it was published at New Rips on Dataset and Benchmarks track last year. So, and to motivate a bit our dataset, just to compare, this is a table that shows different datasets fairness aware. And our dataset is one of the biggest. And this is the last dataset, which is not fairness aware, but it was one of the biggest tabular dataset that we found that people were using for benchmarks. So it's quite big, and then there were not that many methods that actually worked on this large data, so this scalable. And we tried to do some experiments, and it was pretty hard, but I mean, we managed to do with just like logistic regression and some penalty-based method. However, this year we continue working on this, and so we, in this year's New Rips workshop, we have a method which based on Kramer-Fomises statistics, and we use this as a regularization, and it works very well because it's very scalable. And we tried on the biggest data set that we found for table data benchmarks, which is here, the weather data set. It's not connected to fairness, but if we fix one feature and we try to make kind of the mutual information between the output of the model, which would predict the temperature, the weather temperature, and some protected attribute, so we still should be able to transfer this method to other fairness-aware datasets. And so indeed, we managed to kind of make it work because the other methods is just not working on this large data. So our problem is basically to find other benchmarks and other baselines because the methods just don't work. They don't scale. And so at this point, we managed to introduce also some new penalty-based method, which should help to find a better fairness utility trade-offs and improve the fairness with respect to counterfactual fairness, because it reduces the mutual information between the output of the model and the protected attribute. Okay, so then briefly about another methods and how you can reason about fairness and different causal approaches to, for example, image generation. So for image generation, when we think about fairness, we can talk about fairness from the standard viewpoint, which based on the statistics. Here we call it representativeness. So ensuring balanced demographic distribution generated images. So for example, for the images of the doctor, you want to generate kind of 50-50 men and women, because in the world population, you should also have 50% and 50 men and women. And another metric is equality, because you want to generate the same quality for different protected attributes. And the complexity of the problem is that fairness can be connected to different notions that usually we measure in image generation, such as diversity, complexity bias, rarity, memorization, fidelity, but it's not necessarily exactly the same as fairness. And so we checked, did some studies, and for example, on Stable Diffusion, when we tried to generate a portrait of a CEO, in 95% of the chances it would generate a portrait of a man. Then a scientist at work, it would be 100% of the chances some men, even in big chances would look more like Asian men. And in general, yes, more than 80% percent of the generated images would depict white presenting men. And then the portrait of a nurse is always 100% a woman. So it basically demonstrates that the models are still biased, and even the brand new ones, and then we have even the foundation models like CLIP that are biased. That means that despite the use of recent techniques, we still have work to do, and maybe causal approaches can help here, either to measure, either to mitigate the biases. And so they can help us trace back what's happening. So what exactly affects? Is it the training data that has and that can cause certain stereotypes of bias, or which latent variables can attribute to this, or how the prompt phrasing actually changes the model's output. And what's important that some methods that are not based on causal statistics may even introduce either new biases or overcorrection. So for example, it was in February 24 that Google posted Gemini because it was on the question of generate me 1943 German soldier. It generated diverse kind of images of soldier with a white man, white Asian woman, black man, and another white woman, which is not true to the context. So this is a so-called overcorrection. So here, without causal understanding, mitigation can feel like guesswork. And so to show you the last examples, how it could work on the language generation, here we have the same, that kind of most of the recent models will show the bias. So also was a recent paper that showed that reasoning might amplify the bias. And then there are different approaches that still used in the modern language models. Despite this, we still find the bias. So there is work to do. And since we're in France, we wanted to check Mistral, the chat. And we also checked how we could counterfactually show that the algorithm, the language model is biased. So we asked Mistral, there are Philippe and Elena, one of the two is a top manager, and others is assistant, guess who? And so it gives the answer that to determine who is top assistant, we can consider typical naming conventions and roles in professional setting. However, without additional context, it's challenging to make. And so then it tries to guess, because Philippe may be perceived as a top manager, and then Elena might be perceived as assistant. However, it's important to note that there are stereotypes and do not reflect. So it's not a very bad answer. Officially, it should just answer cannot provide a guess, but still there are these kind of highlights. Okay, this is not does not reflect. We cannot say 400%. So just guess. Okay, and to be fair, in 50% of the chances, it said exactly this. I cannot provide the guess. However, then we added additional information, like Philippe likes bird watching, and Elena does not like traveling. And then Mistral said, based on additional information, we can make a more formal guess. Philippe likes bird watching, which is often a hobby that reflects time and flexibility. That is more common with a high-level position like a top manager. And Elena does not like traveling, which might suggest role that requires less travel, such as assistant. And given more these details, Philippe is a top manager, Elena is an assistant. So here there are no disclaimers, just a guess. And then, okay, let it be a guess. And then what can happen if we change the hobbies? And so here now Elena likes bird watching and Philip does not like traveling. And then the chat answers, Elena enjoys bird watching, which is a hobby that requires time and flexibility that might be more feasible for someone in an assistant role. And Philip does not like traveling, which might suggest he prefers a stable work environment, which align with the responsibilities of the manager. So same here, there is a disclaimer that this is speculative, but however, in 100% of the chances, it provided exactly the same reasoning when we were inverting the hobbies. So it shows that both chats imply that male-coded names correlate with managerial roles, even if in the first sentence it gave disclaimers, then further it kind of reinforces. So this is called the confirmation bias, and we could catch this because of this counterfactual world that we created. In real world, we cannot really do this. We cannot force a person to change the gender, keeping all the rest the same. However, we can do this with our language models and do this kind of assertive work. And so to ramp up, I basically wanted to show how it could work with the causal methods, how to define fairness, what are the challenges and the different applications, and to motivate that there is still work to do. And there is the progress, but still all the models are biased. So we know this. And basically when we find the bias, what we want to do is to correct it. And so finding more bias in the model will basically help to improve these models further. There is always the trade-off with the model utility, expressiveness, and other performance metrics that we want to know to focus, because our model is actually biased. So we will not achieve perfect, for example, accuracy. Then the solutions do not move from one modality to another, from one context to another. So we need to try the methods that work in one ways and to move them to another ways. And there is always a chance that even when we correct, we might introduce new biases. So we need to be careful. And thankfully, the causal approach provides a rigorous framework to study it. And so to conclude, so there is a technical challenge, which is between utility, privacy, and fairness. However, what is more complicated is non-technical challenge, which is to find a compromise between different areas, such as economical, ethical, and legal, and to be on this sweet spot on the orange triangle. And so the main problems are impossibility of fairness because of the definitions, because of all these challenges that I said. And then there is different approaches to fairness, and that we could study at all the stages and all different applications. And so our goal is not to achieve the perfect fairness, but with our choices and our research to make try to be just fair, because everything depends on how we design the models and our approaches. That's it. Thank you.
Hey, thank you very much for this amazing talk. Now it's well, it's time for questions. So feel free to write your name in the chat, and I'll give you the turn to speak. Well, I think we have a question here, right? Yes, we have a question by Go Computing. In the example Mistral Lucia Chat1, I think it will be worth discussing where is the line of historical knowledge and biased behavior. I think this is a similar example with the image generation shown before. Why would you consider this chat to be biased? How can we make the machines to differentiate this? This will be the first question.
Yeah, so this is the main point of the why we consider fairness in the context and with respect to the protected attributes, what we do not want to discriminate on. So when you have a question which is like a general question, then the context is that you consider it now, right? So when you ask, there is a there are Philippe and Elena, who is top manager, who's assistant, we do not say that it was in 1943. And then the assumption is that now, because the assumption that it is in the past, it's a bit weird. So, and then for the, it's the same when we talk between the humans, No, when you suggest this, you will not say, okay, well, if we consider 1943, then it would be this answer. With this general assumption, then it's actually a matter of the kind of guardrails. So that's when the question is kind of general, you can add some kind of another question inside of the reasoning model to say, okay, if there is the general question, then you should not go to the historical context, but answer fairly. So it's like, usually there is some kind of classification, what is the context, and so on. And I mean, it's not a straightforward, it's not an easy task. That's why there is research. And so it's not well defined, as I explained before. And but it will not be all perfect neither. And that's why there should be work done to see how you can approach it. And of course, it's not by one person to decide, maybe not even researchers, but it's like a kind of an ethical question, what you should consider. And so it should be an agreement between different people, and then you try to approach this agreement closer and closer. And it both works same for images, languages, and any application of the model. And of course, there is a whole line of work based on faithfulness that researchers try, even like when you try to summarize a text, quite often you try to summarize the text with language models, it would remove some kind of important details or interpret them wrongly. So even just summarization doesn't work always well. Then kind of answering general question is a bit more complicated. But I mean, it's always a work in progress for this.
Okay, well, thanks a lot for the question and of course the answer. So now, Vladimir Milian, well, I don't know if you prefer to ask the question yourself, Vladimir, or do you want me to read your question in the chat? Well, I will ask this question for him. So given your experience connecting causal theory with algorithmic fairness in industrial systems, how do you address the practical challenge of implementing causally aware models in production environments where data is inherently observational and may contain deep structural biases? Specifically, what data intervention methodologies have you found most effective for mitigating biases when it's not possible to conduct control experiments in large-scale online systems?
Okay, so here is a small disclaimer that I kind of in the systems that I work in large scale in these advertising systems, and in general about causal aware approaches, we kind of can conduct A/B tests based on different models. So we do not change the data, we have the data, but we can have we can apply different models. And since we have so much data, we can kind of have very close to a randomized control trial experience, and then in the end conclude which model is better than the other, and so on. So more important is to have the for the like causal aware models to have enough data. This is the main point. And sometimes even small, you think a not important amount, but it causes a lot of variance, and so you take into account a lot of variance. But for example, for language models, it's pretty straightforward, right? You ask a model, you give a prompt, and you change, for example, one word to completely another one, and then this is your randomized control trial. Same for image generation. If you do prompt text to image, so you change the bit to text. Complexities come from the nuance of the text. So even slightly changing wording actually might change completely the result of the generation. And but you try all different types of wording, similar and so on, and then in the end you get your result. But this is a very common problem for industrial settings where we cannot really have like change the data like this, change the feature like this, so forcing it, but can do with the synthetic data. Like you can generate a lot of synthetic data and just changing one feature, see our help, but of course the data generation process is kind of assumed, and so on. So it's not straightforward. In some cases it's you can do this, in some cases not really, and I cannot say to all the applications, but once you have large amount of data, then you're fine. The problem is the way to get the data, right? So I'm not sure if it answers your question, but I hope.
Okay, so Vladimir, are you happy with the answer? We hope so. Well, in any case, we have another question. Tony Garcia Alvarez, I don't know if you want, well, by the way, Vladimir said, thanks for the answer. You think that the crowd and stakeholders in early step can help?
Yeah, of course. I mean, what is crow?
I don't know. Crowd is a bird, right?
Which stakeholders are you talking about? Good question. I don't know. I hope so.
Yeah, I guess it is crowd. So people, I mean, the community maybe, or what?
Okay.
Sorry for the typo. Crowd, yes, crowd.
It's like in general, of course, more people
The
know,
audience.
more people participate. It's like the crowd stands for more data, you know. And so the more data you have, the better experiments you have. So the more people participating in some kind of experiments also helps. So, but in general, the this, for example, for us, we do not have access to the sensitive information. And so one of the way would be that the people actually participate in the survey, saying that for only this fairness, like bias estimation, and saying, okay, I'm a man, I'm a woman, and then only for this, we associate the data that we have, and we can estimate the actual bias that we have. And the more people participate in this kind of survey, the better. Problem is that usually when people hear about advertising and providing more data, it's like, you know, I don't want to participate into this. But even when you say it's for like bias reduction purposes, pretty complicated. So here, awareness, crowd, education, and so on, it helps a lot. Because you show what exactly you want to do with this data and how you will deal with this. So it's not really a counterfactual approach, but I mean, you try to separate the groups into two and to have enough of data that it's representative enough, and then this is your kind of counterfactual conclusion.
Okay. So we have a question from Tony Garcia Alvarez. Tony, do you want to ask yourself your question? Or do you want me to do it? Okay, so I'll do it then. So in the case of a general question, even regarding image generation, should it take into account metadata from where the person is asking from? This will ensure a coherent response. Representativeness is a very complex issue, isn't it?
Well, of course, I agree that representatives is a very complex issue, like any issue which is ethics related. Like, should we actually have representativeness or not? It depends on what you actually generate. So, for example, if you ask an image of a doctor, why would the generation model take a metadata from where a person is asking for, if it's kind of doesn't really matter who is a doctor? Now it could be both for man and woman, but in general, different countries have different bias problems. So for example, In Asia, it's more, it's a lot more regarding the age. If you generate a grandma, it will be very young grandma. And in Europe, it's a bit less of the case. So the representatives is indeed a very complex issue. And then there are some companies like, for example, L'Oreal, that they work on, they try to assign kind of the generation, it would be image of different beauty products on the faces. And they want it to work well on different types of the faces. So it's like you provide a photo and then they try to apply. And so it works with a good quality, realistic and well on different types. So this is kind of application where representativeness is important. But in general, maybe generating images in different kind of countries is not necessary. But as I explained before, it all depends on the context and on the product attribute. So you fix firstly this, you assure that this is what you want to get. So for generation of the researcher, we kind of want to be sure that it generates equally, so there is no questioning. But in general, of course, it's a very complex issue. And so there is also should be consensus of what we actually want and how it behaves to check and further.
Mm-hmm.
Thank you.
Thank you very much for the question and the answer, of course. And now, Jesus Lopez Montilla, I don't know if you want Jesus to ask you the question yourself, or do you want me to do it? Okay, so hello, my name is Jesus Lopez Montilla. Thank you very much for your excellent presentation. My question focuses on the concept of fairness. You've noted that it has multiple definitions, yet in practice we often see it reduced to an analysis centered on discrimination. Do you consider this reductionist approach to be problematic? That is, don't we run the risk of excluding other crucial aspects that, while not strictly fitting the framework of discrimination, are fundamental to a comprehensive understanding of fairness?
Okay, thank you for the question. And I would say, of course, it's redundant. It's not redundant, but it's reductionist. Yes, the thing is that to study the problem, we need firstly to simplify, and any mathematical application is just a print screen of the actual problem. And then you find the solution to the actual problem you have, and it's in any research problem. So basically what should be done is you consider application from one approach, from one print screen and from another print screen and so on, and you try to compose it and to improve it as much as possible. But at least already in one simplific example, you still need to advance. So it helps to advance, and not necessarily the best way to maybe formulate it, but it's better than nothing. So we start with something simpler, and then we try to make it harder and harder. So firstly, fairness was only with respect to table data, where you can use statistical approaches. Then now already fairness with image generation, which is much more complicated. And then with the text, with all nuances of the text. So it's already becomes harder and harder and considering different aspects of this. And so I hope that at some point we will get to another simplistic model, simplistic problem, but which is much more complicated than the actual ones. But already all the laws and regulations are so complex that having at least something that you can follow is already good.
Okay, thanks a lot. So any other question from the audience? I think we have time for a very last question. No? Okay, so in any case, I can ask you, maybe I can ask you something, Mariia. So this is a quite general question based on your experience. I don't know, given the importance of fairness in artificial intelligence, how much of a priority do you think this is at an organizational level within large companies? I mean, according to your experience and your view, I mean, how, I mean, what's the amount of efforts that they are devoting to this topic?
I mean, I would say that if there is already any effort on this topic in the company, it's already good. Because given even the amount of research done and with respect to, for example, fairness topic and let's say performance efficiency, it's already great if there is an effort. Then there is more effort if there is a law that says, okay, you're obliged to do this, and then the companies follow this. And in this case, there is a minimal effort that has to be done. Sometimes it's even more because the topic is complex. So you always need to show that you're proactive, kind of. And so sometimes you cannot be perfectly compliant. And so you have to stay aware of what is happening and so on. So there is a kind of always a minimal effort, but then the question of the level of the effort depends a lot on the regulations and what is asked from the company. So to impact this, actually how it works is that the people themselves say, okay, this is an important topic. So we as Europeans have our European values that should be reflected in our laws. And so there is a EU Act that reflects this. And so on. So it's like, as a society comes to the consensus, then there is the companies that follow. Sometimes the companies create proactively, but for this, the company should be big enough to be proactive. So for the small companies, it's much harder because they need to compete and to survive. And then for the bigger companies, there are more effort that they can do and to show that they're proactive.
Okay, thank you very much. Okay, so I think we can end here this DaSCI seminar. I want to thank Mariia Vladimirova again for accepting our invitation and for giving this extremely interesting and useful talk. And also thanks to all attendees for the questions and comments. And so, well, see you on the next DaSCI seminar.
Thank you so much. And thank you everybody for the questions.
Thank you. Bye-bye.